Okay, the recording is started, I guess. Okay, so I will switch to my document camera. So today we have eight topics. So the first topic will be the introduction. We will talk about what are we going to cover this semester. The second topic will be how to do it. So we want to control something. Nobody wants to be controlled, right? So everybody wants freedom. But fortunately, we are not controlling people. We are controlling process. So that's our topic, process control. So we are controlling a process. So how to do it? That's our second topic. The third topic will be the components. So we want to know how to do it. What are the components? 5 different components. The next topic will be if you design a control system, how do you evaluation? So is that a good one, or average, or terrible? Right? Evaluation. Of course, our evaluation is technical. It's not about the money. There's another evaluation, obviously, how expensive. Maybe we should add that. But the author didn't have that. So maybe we have a break after the fourth topic, and then we will talk about the evaluation of control systems. It started 50s, 40s, analog, but we have a digital revolution. Everything is digital, so our control will be digital. Talk about this evolution of digital. The rest of the topic will be some common subjects related to control, but something you might already know. So they talk about standards, they talk about the units, and then we'll talk about the time response of a sensor. We will start talk about one of the components of this control system. So we talk about components. One of the components, very important component, is your eye, right? If you want to control something, you have to see it. Otherwise, how do you know the results? So that's our eye for the control system. How fast you can see the results. The last topic will be 2 topics related to math, right? It's called significance and statistics. When you want to control, you cannot completely avoid math. We actually avoided calculus. So this class, we already avoided calculus, but we cannot completely avoid math. We talk about it. Oh, okay, introduction. What? Well, this is what we're going to do all semester. There is kind of like a delay, but so this is what we're going to do all semester, is trying to maintain this level. Can be a temperature, can be humidity, can be pressure, can be flow, how fast you pump. It doesn't matter. We want to maintain a constant level. How do you do it? So this is what we're going to do. So that's our first topic. But how do you do it? Second topic. How? How to do it? Well, humans have been doing this for thousands of years. That's how we do it. We just hire somebody, right? Well, people are expensive. You have to pay him wages. And also people can be tired, fall asleep, make a mistake. So this works, but this is better. So as technology get evolved, we actually figure out how to do it automatically. So that's called so that's what we're going to study. So instead of having a person, we will have the eye, the muscle, right? The muscle, the brain. So this literally replaces a human being. So this is the brain, this is the eye or ear, this is the muscle, and that's the same valve instead of controlled by people, a person, it will be controlled by actuator. So that is what we're going to do and how we're going to do it. So we will study each component. There's a two type of control system. When we talk about control, generally there's two different types. The first type is called the discrete control system will be acted like a timer. It will turn something on and off in a sequence. So it will be a sequence of events. A perfect example will be the dishwasher. So I know everybody doing dishes, right? The dishwasher. So if you listen or observe how a dishwasher works, it's just a sequence of events happening for those 2 hours. So it takes about 2 hours, but during those 2 hours, there are timers to turn different components on and off. So that's called a sequence event. That is actually not our subject. This book, we are not talking about a dishwasher. So what this book will cover? We will talk about pizza ovens. So yeah, actually, this book will talk about the process control. One of the process control we use every day is the pizza oven. When we bake pizza, it's same thing. So instead of calling it pizza oven, we call it process control. So this book is a process control. Just remember, it's the same thing as your pizza oven. So this process control generally control a process. In the case of pizza oven, we control the temperature of that oven, right? In the industrial or commercial settings, it's not just temperature. It can be, we want to control the flow. We want to control the temperature, humidity. pressure. So we want to control a lot of things. Typical industrial setting, we might want to control 20 different, a few dozen different process. So in a factory setting, we are talking about 20, 30, or 40 of those controls. 20 or 30 of those controls. So we call it a process control. So what is a process? So a couple of definitions. What is the process? A process is a variable which can be controlled. A process is a variable we can control. So a temperature is a variable. A flow is another variable. So multi-variable. So we want to control those variables. So that's a process. A combination of all those are called a plant. So a plant might control that may have 20 variables we want to control. So when we're cooking cat food, for example, you might control the pressure, the temperature, the flow, whatever. So that's called a plant. What are the components? Number 3. We're going through pretty fast. We're already on the 3rd topic. The component of your system. What are the components? 1, 2, 3, 4. 4 components. So a control system, a process control system for a single variable. We are talking about a single variable. For a single process, we're talking about the 4 components. And I listed, we started with this one. The first component are called measurement. We will talk about that in 3 chapters. Chapter 4, Chapter 5, and Chapter 6. So we will have 3 chapters cover the first component of our control system. And then Chapter 7, we will talk about the muscles, control element. That's the eye, that's the muscle. So we have 1 chapter, Chapter 7, talk about the muscles. Then we will have Chapter 9, Chapter 10, and Chapter 11. We talk about the brain of the control system. So if you look at our textbook, we have how many chapters? We have 12 chapters. So out of the 12 chapters, 7 chapters are here. 4, 5, 6, 7, 9, 10, 11. Those are the key chapters, plus chapter 1. So chapter 1 plus those chapters, chapter 1 will be the overall introduction. And then we will go into those chapters, cover each component. So that's our plan for the semester. We might stop at chapter 6 or 7, have our midterm. After the midterm, we will continue. We might stop at chapter 6. So we have a midterm. So those are the first half. And then we have a second half. Started chapter 7. So this is called the block diagram of a control system. If you noticed, this control system form a circle. So that's every control are called a loop. So a plant might have 20 loops, right? 20 loops. That is one of the 20 loops for a plant. This is a block diagram. So this loop is represented using what we call block diagram. The loop can be represented many different ways. That's one way to represent a loop. Block diagram. So block diagram. How do we, is there any other way to represent the loop besides block diagram? Yes, there are many others. What is the most common? What is the standard? The standard is called this is the standard. So the same loop, instead of block diagram, this is called P and ID, piping and instrumentation. So we'll talk about that later, but I just pointed out a single loop can be represented by many different ways: block diagram and piping and instrumentation diagram, P and ID diagram. This is the standard diagram. So if you want to be a control engineer, that is the language you spoke to another control engineer. Piping and instrumentation diagram. Well, alternatively, another way to represent the same thing is called a physical diagram. This is a physical diagram. So we have a block diagram, we have a physical diagram, and we have P and ID. So these are the three most common tools we can use to represent a loop or represent a control process control, one process control. So let's look at the physical diagram. The physical diagram is kind of like a picture of what's going on. So it's not a realistic picture, but it's pretty good for engineers. So I can draw this. I cannot draw the realistic. So this is a flow control. So this is a pipe. We are pumping water, pumping oil, or pumping gas, whatever material you are pumping. And how do we control the flow? So this is the valve to control the flow. That's the sensor. So this is the eye. The sensor will measure the flow. What is the output of my sensor? It's pneumatic output. So this is a typical sensor with a pneumatic output. The pressure will be 3 to 15 psi. So the minimum pressure, the sensor output will be 3 psi. The maximum will be 15 psi. So this psi, the pressure represents the flow, like a gallon, 1 gallon per minute, or 10 gallon per minute, whatever. So this sensor output will into our second component. What is second component? Second component called the pressure to current converter. So this is a standard module. We'll talk about how to build one of those later chapters when we talk about pneumatic devices. Anyway, you can buy one of those off the shelf. It will convert the pressure into current. And this is the standard pressure. This is standard current. Current will be 4 to 20 milliamps. So sensor, converter, and after we convert the pressure into milliamps, the milliamps goes into electronics controller. So we are looking at some electronic components. And this electronic component will be the brain of the system. And this brain has a boss, right? The boss tells the brain how much flow. So this is basically the operator will set the set point. I want 10 gallon per minute. I want 100 gallon per minute. Whatever the operator wanted, he will set the set point. So the controller will make a decision based on the set point. The decision will go to the muscle, right here, muscle. The decision is another current. So that's a typical controller, a current in, current out. Current in, current out. But this muscle do not recognize current. This muscle is a pneumatic muscle, pneumatic actuator. The actuator wants pressure. So again, we have another controller called the IP converter. IP converter. The IP converter will convert the current into pressure, and that pressure will open and close in this valve. So that is a control system. We call physical diagram because it's closer to the physical device. So that's another way to represent your control system. So that's the block diagram. That's your physical diagram. And if you want to map from physical to block diagram, we will do the mapping. Okay. This block right here, right here. And then, let me see. No, this block is here. I'm sorry. Right? Yeah. Yeah, the author make a mistake here. It said the PI, not IP, right? PI. So this block is right here, right here. So this physical component is represented right here. And then next component will be the controller. The next component will be the actuator. And the pipe and the flow will be the process. So this is the block diagram. We are mapping one-to-one. That's the muscle. That's your process. That's your sensor. That's your brain. That's your brain. All right. That's our third topic. Next topic is evaluation. How do we evaluate? What is a good system control? What is the average? Well, it's all depend on the requirement. So there is a three way to evaluate. First evaluation is it stable? Second, is it accurate? Third, is it fast? So when we want to evaluate our control system, generally we evaluate with three criteria. Criteria number one, if it's stable. That's called stable. That's called unstable. Right? Unstable. So this is unstable, obviously. That's a control system completely failed. Completely failed. So when you're cooking cat food, right? Your cat food will be either too cold, undercooked, or burned, right? Overcooked. So that's unstable, lost control. So that's number one. Obviously, we want a system which is stable. Second, well, even though your system is stable, but how accurate, right? Accuracy. It's all depend on the requirement, your customer. Your customer will decide how accurate you want your control system. For example, when you're baking pizza, you set temperature to 350 degrees, right? Is that how you bake pizza? 350? 400? Okay, 400. You like crispy, right? So 400. How about accuracy? Do you worry it's 5 degree off of 400? Or 10 degree off, or 50 degree off? 50 degree off may be not acceptable. So accuracy is another thing. Plus or minus 10 degrees, for example. That's what I want my pizza oven have to be within that limit. If it's off limits, you may need to buy another one, right? So accuracy, it depends on your application. Another application is room temperature. Everybody is stay inside, air conditioner. How about this? Will you accept plus or minus 10 degree for your air conditioner units? No? Too spoiled. So yes, we are spoiled. Maybe plus or minus 2 degrees, okay, right? Yeah, I can handle 2 degrees. I can handle 2 degrees. 2 degrees. But 10 degrees, maybe it's too much. Different application has different accuracy requirements. I give you a very extreme example. Everybody know hard drive, right? Hard drive. The hard drive, what is the capacity of the hard drive? When I was your age, it's 10 megabytes. When I was 15 years old, it's 10 megabytes is the cutting edge. Cost $1,000, right? But now it's 10 giga. It's a million times. Is that right? A million times? No? 1,000 times. So 1,000 times. What does that mean? That means the tracks are more tight. Also, it gets smaller. When I was your age, 10 megabytes is like this big. Now it's tiny. So there is a control system control which track you read and write, right? Which track? It's closing to nanometers, right? We're talking about really accurate controls. So we are talking about very, very accurate position control. That position has to be accurate to millimeters. No, cannot make it because that's too much. It's like a needle. We want to find a needle. So we want to really accurately find that needle. How fast? In the case of hard drive, what is the speed you want to find that track? So you click on your document. For example, you have a semester project, you write a PDF document, you double click, you want that appear on your screen, right? Instantly. So in the hard drive, we are talking about milliseconds of speed. So you want to find track number 10. That control system have to find it within milliseconds. How about your house? You're cooking pizza. You set it at 400 degree. How long you have to wait for your pizza oven to reach 400 degree? Milliseconds? I hope so. I hope I have that kind of oven. Milliseconds doesn't exist. Maybe 5 minutes, right? Yeah, 5 minutes. That's realistic. 5 minutes. So that's what we are talking about. We want to reach our target. Sometimes we want milliseconds. Start it from here, end it here, milliseconds. Sometimes we're talking about 5 minutes. 5 minutes. So that's the speed. And how do we reach our target? There's two ways, two methods, or two response to reach our target. This response number one is called damped response. Damped. So this is a damped response. A lot of our control systems are damped response. Well, alternatively, we can have our second response. Second response called oscillating. Cyclic. So we might also have a cyclic response. So that's a cyclic response. Which one is better? Well, generally, if you want speed, that's called overcorrection. But you want fast. Like if you want to drive from here to Kansas City, you want to drive it really fast. You really drive it fast. You drive it so fast, you actually pass Kansas City. So that is how you drive. Like a bad driver. You drive so fast, when you brake, you pass Kansas City. And then you do it a couple of times. Finally, you reach Kansas City. So you drive forward and you backwards and backwards. That's backwards. But you back too hard. And you forward again, backwards. Finally, you reach Kansas City. That's terrible. But actually, that's a good way to control when you want speed. In many control systems, that's how we do it quick, how we do it fast. Kind of doesn't make sense, right? If you drive, it doesn't make sense. But we're not talking about drive. We're talking about, for example, the hard drive, finding the right track. So you find it pretty quickly that way. Of course, this is always good. Many systems, for example, the room temperatures, might do this. So that is damped and cyclic control. That's the first full topic. How long? 40 minutes. Anybody need a break? I didn't see you falling asleep. I'm still So maybe we just maybe we do have a break because there's a lot of material follow. So let me pause my recording and you guys whatever you want to do, grab a drink, right? That's the nice thing about taking class at home. You have all the comfort of home. All right, I will pause. Let's do 5 minutes, 45, yeah, back 45. All right, let's continue. That 5 minutes really goes fast. Maybe we need more than 5 minutes. No? Anyway, I can see, so maybe we need more than 5 minutes or not.
I'm here.
Enough for your team?
I'm ready.
You're ready, okay. Okay, all right. I actually talked to my son and daughter about, because they are in college also. I asked them how do they feel about this online Zoom meeting lecture. My daughter actually liked it. She says she can concentrate more than in-person class. I don't know why. She says she always daydreaming something else in class. Also, she says she prefer watch offline, not taking the class same time. She watch 3 or 4 together. She says that helped her to concentrate her study. So spend the whole afternoon or whole night, 3 or 4 lectures watched together. Help her really concentrate study, help her understand the material. That's her. But I felt it's okay, almost like a real in-person, face-to-face teaching. Especially, I can saw a couple of faces on my screen.
Right.
Yes.
I think for our classes, they're better in person.
Better in person?
Especially for the labs.
Yes, the labs is needed. I agree. Yes. But for the lecture, how do you feel about the lecture?
I think I'd still prefer in person, but the Zoom isn't bad.
Yes, that's the second best. That this technology getting really okay. Yeah, it's Zoom. Right. Yeah. It started like 10 years ago. Online chatting. The webcam follows the mic. That's the technology. Whoever talks, the camera switches.
Right.
That's and then with this sharing, I really like the sharing. Yeah, recording. Yeah. Okay. Let's continue. So our next topic will be this evolution from analog to digital. Analog controller is still used, very, very commonly used. So it started, like I said, in the 30s, 40s, and the 50s. At that time, we don't have computer. All the computer is a multi-million-dollar equipment, big and huge. So most control started as analog controller. Even before analog, we have a mechanic or pneumatic controller. So even the analog controller can be pneumatic or mechanic. The mechanic controller, a perfect example will be your toilet, right? Everybody had a bathroom break, right? 5 minutes ago. And your toilet is a perfect example of this control system, which is all mechanical. There's no electronics. It basically keeps your water level and not flooding your bathroom. You know, you'll never worry after you flush your toilet. You never worry the water will be overflow because the mechanic system will shut off the valve. Another analog will be pneumatic. The pneumatic controller, we will talk about that in chapter 10. So the analog controller can be electrical, can be pneumatic. The pneumatic controller is still used quite often. I give you an example. You are using it probably right now. If your air conditioner is turned on, there are pneumatic controllers in your air conditioner system. It's called the TX. I'm not a conditioner guy, but it basically control how much freon you are pumping. Yeah, how much freon you're pumping. So that is a pneumatic controller. We'll talk about that in chapter 10. You have a needle. The needle will go in and out, which control a valve. The valve will control how much freon goes into the evaporator coil. And the sensor is a temperature sensor, which is a pneumatic sensor. The sensor is a capillary tube. So the sensor is attached to the evaporator core. It measures the temperature. So if I want more coolant, the sensor will sense in the temperature is not enough, so it will automatically open and close in that valve. So that's pneumatic control. So there is a lot of analog controllers. So analog doesn't mean obsolete. Analog means simple and reliable. A lot of time, if you want a simple, reliable, we still have the analog controllers. Of course, a lot of analog controllers are electric. Electric analog controllers are more common. At least for us, we are electronics program, so we are more comfortable with those electrical analog controllers. Electric analog controller, let me give you an example of electric. Those are electric analog controllers. Part of it, that's the brain part, brain. So if you look at it, it's a bunch of op amps, right? Op amps. Operational amplifier. It will do a mathematical calculation. So those amplifiers will add, will subtract, will integrate, or differentiate. Another example. We will do addition. This is addition, and subtraction. This is subtraction. Addition, subtraction. This is called the integration. This is the differentiation. And then this is addition. So we have 1, 2, 3, 4, 5 operational amplifiers. And they each will do a mathematical calculation. And the end result of that mathematical calculation will be the controller output. So that's my controller input, that's my controller output. So this is how op-amps got name, operation. No, that's mathematical operation. So that's analog control system, still widely used. Well, then came the digital. Everything is digital. So why? Because it's easy. Okay, the technology develops because millions of people work so hard. Not only the digital actually is easy now, it's inexpensive. How much does like I said, this controller, PID digital controller, $20, the whole package, $20. Well, that is actually an off-the-shelf digital controller. I also said I built one myself. I will show you the one I built. It's in my office right now. I will bring it over to my house, to my home. How much does that cost? I built it myself. Make a guess how much they cost.
$5.
$50.
50.
$50.
So it costs more for you to make it yourself than to just buy one.
In that case, yes. I make a mistake of using the $50 processor. So it's all depend on the computer. So the computer I used, unfortunately, is a proprietary computer system. They sell it for $50. So the controller is $50 because the computer I bought is $50 computer. So alternatively, I can use a $1 computer. Can I use a $1 computer? Yes. Actually, that $50 computer is $50 only because the software. The hardware is 50 cents. That $50 computer, the processing unit is 50 cents. They put a operating system, put a programming language into that so I can use it easier. And they sell it for $50. So you can do $50, you can do $1,000 if you use Apple Macintosh MacBook. That will be $1,000 computer, right? Or you can do $1. $1 controller is my favorite. I have 8 of those around my house. 8 of those. Let me show you my $1 one. It's under the table, so I will crawl under the table, grab my.
All right.
Well, this is my. Actually, it's $5. I bought it $5. The processor inside is $1. The processor inside. So if you open it up, I actually opened it up. There's a couple of screws. You opened it, and there's a little microcontroller. It's $1. It has Wi-Fi built in. This $1 controller is perfect for this. This is a Wi-Fi switch. I have 8 of those around my house. I use it every day. I turn on my lights, outdoor lights, indoor, outdoor, turn on the air conditioner or heater, and also a dehumidifier, on and off, using my cell phone. This is Wi-Fi controlled, so I can, using my cell phone, to turn this thing on and off. This is my favorite controller, Wi-Fi based controller. Actually, $1 is the lowest. Generally, you can get those like $3 on eBay or Amazon, and then you wait for a month. If you want the $1 one, probably they ship it out from somewhere in East Asia. So everything became computerized because we have this $1 miracle computers. Not only it's $1, it's Wi-Fi. Wireless. So this controller can be wireless. It's wonderful. Wireless is huge. So I don't have to have any wires to control a device. This is Wi-Fi, need a little bit of power. What is the alternative to Wi-Fi if you want a wireless? Bluetooth, right? Bluetooth. Bluetooth is low powered. I see like a $1, $2 wireless Bluetooth sensors or controllers powered by solar. So basically, you just throw it in your backyard, and you can measure your soil, your moisture level of your backyard. Like you really like your lawn to be beautiful, measure the whatever you want to measure. It's powered by solar. So we have a local factory called Gray Manufacturing. We have a field trip a couple times. Did you ever go to Gray Manufacturing? They're cutting edge. They are called the Cadillac of car jacks. They make car jacks, the big ones, like an 18-wheeler, the big trucks. So their car jack is wireless. So what kind of wireless do they use? They use this. This is another standard wireless technology, Zigbee. The nice thing about the Zigbee, it's called mesh or peer-to-peer. P2P, peer-to-peer. They don't need a hub. Right? Wi-Fi, you need a hub, right? That makes things complicated. Peer-to-peer, so each jack can talk to the other jack. So your truck will raise and lower same time, right? Not upside down, one side go faster than the other, your truck will be flip over and somebody will get hurt. So that's Zigbee. We have a lab on that. I still work on the labs, so we might do one of those. Zigbee. Right now, the Gray Manufacturing outsourced this technology very expensive consultant do this work. So hopefully after taking class, you walk into green manufacturing and said, hey, give that money to me. I will do it for you. Zigbee. And control. It's all simple control. It just control the 4 jacks up and down. How complicated can that be? On your cell phone, we will do it on cell phone also. We will control something on our cell phone. Not this class. I'm not sure the lab, but in another class, my computer class, 4.2, Advanced Computer Design, we actually control from our cell phone. Just like the green manufacturers, their cutting edge car jacks are wirelessly controlled from your cell phone. And they pay tens, if not hundreds of thousands of dollars for the consulting fee. Right now, it's a company from Boston, from Massachusetts. It was a professor from Oklahoma. They switched a couple years ago to another. I'm not sure right now who is getting that paid, but I think we can do it locally. We have the ability to control 4 car jacks moving up and down same time, right? So that's analog to digital. A lot of advantages for digital. So that's why everybody moved to digital. Even a car jack is computerized, digitally controlled. Right, let's move on to our next topic. Will be unit and standards. Now we will start some math. Everybody likes math, mathematics, my favorite subject. Yeah, I'm true. I'm not lying. My favorite. I was a kid. I will study math all the time, and do the math competitions. So does my son and my daughters. It's like a gene, math gene. My son and daughter represent the states to do the math competition in United States. Anyway, units, standard units. Now, this is something everybody is familiar with. This table. Oh, what's wrong with my camera? The light is too much, yeah? Too bright. Okay. So those are the units. When we talk about length, mass, time, we talk about electrical current, temperature. Okay. Well, how about the control? What kind of unit do we use in control system? Start with pressure. Start with current. Current. We use current quite often in control system. More particular, we are talking about a current of 4 to 20 milliamps. Yes? A question? Okay. I heard some current 4 to 20 milliamp. In a control system, when we talk about current, we talk about standard current. Standard current. We're not talking about this guy. This guy says 100 amp. 100 amp. Oh, I was just bragging. It's maybe 20 amp. This guy can handle 20 amp. We're not talking about 20 amps. We're talking about milliamps. 4 to 20 milliamps. So that's a standard current control system. So that's number one. We want to measure. We want to use is the current. Number two is the pneumatic. Okay, now it's better. Let me turn on my light. Number two is pneumatic PSIs. So pressure. I like to write something on the paper. It feels like in the classroom, I write something on the whiteboard, right? And I've also felt when I write, it's the best way to teach is I talk and write. Why? Because that will slow me down. Because I can talk, but if I write, it takes more time. And that will keep the perfect pace. Otherwise, when you only talk, you go so fast, like light speed. When you write it down.
Do you have a ceiling fan in your room? Because there's like a weird clicking noise that keeps going off. Does anyone else hear it?
I'm not hearing it. The only fan turned on is my computer. My computer is overheat. I guess I'm teaching too hard. My computer is overheat.
Yeah, because I heard after we came back from that little 5-minute break is when it started happening.
I keep hearing it too.
Oh, my.
Well, it's fine. You'll hear it. If you watch the recording, you'll hear it.
Yeah. I'm sorry, I don't know what's going on. I don't hear anything in my room. Except the fan is the computer is maybe the aliens are hijacking us, huh? Those technology is out of control. Nobody knows what's going on.
Dr. Zhang?
Yes.
I have physics, so I have to go.
Okay, no problem. Watch the video.
Yeah.
All right, Jeremy, Jim.
Right.
Yeah.
See ya.
All right, bye-bye. So pressure, we are talking about 3 to 15 psi. 3 to 15 psi. Let's do one example. This is example 7 from the textbook. So let me zoom in a little bit. All right. So we got a sensor. So we want to measure 20 to 120 degree. And this sensor will measure 20 to 120 degree. And the output when the temperature is 20 degree will be 4 milliamp. And the output when it's 120 degree will be 20 milliamp. So this is my sensor. 20 degree, output is 4 milliamp. 120 degree, output is 20 milliamp. Now, here's my question. if my reading is 12 milliamp, what is the temperature? 12 milliamp, what is temperature? Temperature? 70 degree. How did I get the 70 degree? How did I get that answer?
Well, isn't 12 milliamps right in the middle of 4 and 20 milliamps? So the temperature, what?
Perfect.
Oh, okay.
That's the perfect answer. Perfect answer. Well, there are mathematical equations, but the way you think is like an engineer. That's what I like engineer to think. Because you can have all the mathematical equations, but if you are in the field, you want answers. You don't want 10 mathematical equations, right? So yeah, perfect answer. I will draw this. A triangle. 20 degree, 120 degree. Horizontal, vertical, 4 and 20 milliamp. So that will be my triangle. If my reading is right in the middle, my output will be right in the middle. Craig, you said it perfectly, right? That will be 70 degree. 70 degree. All right. How about 5 milliamp? 5 milliamp. What should be temperature for 5 milliamp? Then it's not so easy, right? Not so easy. So in order to find out the temperature at 5 milliamp, we have to find, we have to use this equation. We have to use this equation. That means 120 subtract 20 divided by 20 subtract 4. That is our first equation. 120 subtract 20, 20 subtract 4. Multiply what? 5 subtract 4 plus 20. So that's the equation when we have 5. So if my measurement is 6, I just replace to 6. Everything else will be unchanged. Everything else unchanged. So let's do the math. What about 5? 5 will be 100 divided by 5 milliamp, temperature 26.25. How about 6? 6. How about 12? we use this equation to verify 12 is correct. 12. So, all right. So that's the equation. This one is the only number need to be changed. So if it's a 6, it's a 6. If it's 12, you put 12 here. Everything else remain the same. The author said 6.5 milliamp. What about 6.5 milliamp? 6.5 milliamp. Yeah. It's 6.5, it's 35.625. 35.625. So whatever current reading, we can convert it to temperatures. Okay. This is the first mass. The second, this is 1.6.1. 1.6.1. 1.6.2, we'll talk about the accuracy. So when we design or when we given specs, we want the accuracy. We want to define accuracy. So accuracy, for example, plus or minus 10 degrees or plus or minus 2 degrees. Now that's the accuracy we required. Accuracy required. So so if I say I have a sensor and then I have a control and I have a actuator. The sensor's accuracy is plus or minus 1%. The controller accuracy is plus or minus 2%. The actuator accuracy is plus or minus 3%. Okay? So what is the accuracy for the whole system? Accuracy for the whole system, right? That's when you design something, we are not using one single component. We are talking about multiple components. When we are using multiple components, everybody contribute to some error. Like you tell your friends something, your friends tell your friends, and then your friend tells another friend. After 10 friends come back to you, is that the same thing you tell your friends? Same thing happens here. Everybody add some distortions to your original signal. So, so what is the total accuracy from here to here? 1%, 2%, 3%?
Is it plus or minus 3%?
3%?
Yeah.
But that's the actuator alone. The controller will have, you add up. All those errors will add up. It will be more than 3%. More than 3%. So there are two ways to find the accuracy. First, it adds together 6%. Plus or minus 6%. Plus minus 6%. That's a rough estimate of the total accuracy of the whole system. So you have, you tell your friend something, your friend, tell your friend it's distorted, and when they return back to you, all those distortion came back to you, right? So 1%, 2%, 3%, 6%. Alternatively, we can use another equation, more accurate, but more mass. This equation. So what is this equation? The accuracy will equal to 1% square what does that equals to? (1% square plus 2% square plus 3% square, and then square root. All right, square root. That is 1 plus 4 plus 9 and Tim, you are almost right. 3.7%. 3.7%. So the accuracy using second equation, which one is better? This one is more accurate. This one is more accurate. This one is a rough estimate. In the field, you don't have a calculator, so you just use the first method to get a rough estimation. When you are in your office, at home, you have a computer calculator, use the second method. It's more accurate. So the combined accuracy is 3%. So what is the 3.7% means? It's plus or minus 2 or 10? Well, you don't know. You have to do the range. That's maximum. If the max temperature is 100 degree Fahrenheit temperature, then plus or minus 3.74% translates to plus or minus 3.74 degrees, right? Yeah, 3% of 100 is 3.7, right? 3.7%. So that means your temperature, if your measured temperature is 100, then it might be 3.7 above or 3.7 below. All right, that's our second topic. The third topic will be a big topic. This is our third topic, PNID. It's called the piping. It's called the piping and instrumentation diagram. Piping. Piping and instrumentation diagram. When the control engineers design a control system, they draw P and ID diagram. And this diagram basically is how they communicate with each other, how their control system is designed. For example, this one, the first letter, this one has one loop, two loop. No, one loop, two loop. So this is a two loop control. One loop, another loop. The loop number one started with a capital T. T, right? So the capital T means temperature. So the first loop controls temperature of this reaction vessel. The reaction vessel might be a pressure cooker for cat food, right? Our local South Shenzhou, we have a pet food manufacturer. And that's one of their cooking vessel, for example. And you want to measure the temperature or control the temperature. So that's one, temperature. T means sensor. C means converter. So temperature converter. Now this is a converter. So that's temperature sensor. This is a controller. I'm sorry. C means a controller. That's the sensor. Temperature sensor. Temperature controller. Converter. Temperature valve. And the steam goes in. If the vessel temperature is too cold, and what happens is this valve will open. The steam will coming in. More hot steam will raise the temperature of your pressure cooker. The second control is called F. F is flow. So T, temperature, F, flow. T, temperature, F, flow. All right, let's look at the flow sensor. Flow controller. Flow controller valve. Recorder. FR, what is FR? Flow recorder. All right, they also have numbers. 302. This is a loop 302. We have a loop 302. What about the other loop? Loop 301, right? Loop 301. We have two separate loops on this plant. One is a temperature loop, one is a flow loop. What about this? Holding tank. Holding tank. This is a level. So this is a level sensor, level controller. The level sensor and level controller decides is the input for a F controller. So we have two controllers. This is called a nested loop. Nested loop. So you have a loop, you have a small loop, inner loop. Okay. You have an inner loop. Which control the flow. And then you have an outer loop which control the level. You also have a third controller control the output flow. So this holding tank, we pumping material into the tank with this flow controller. So this flow valve will control how much material will pump into the storage tank. The third controller will control how much we pumping out of the tank. And then this inner loop and outer loop together control the level. So that is a control system. It's more complicated because you have an inner and outer. So P and ID. What if I want to know more about P and ID? You go to page number 619. 619. All right, 619. 619 tell you everything you want to know about all the symbols of this diagram. Basically, like you learn a foreign language. That's all the vocabularies. Like you can speak this language after you learn all the vocabularies. All right, let's look at a couple of vocabulary. Electrical signal, pneumatic signal. All right, let's look at the electrical or pneumatic. So this is electrical. This is pneumatic. You can also have hydraulic, capillary tube. So that's our first symbol. Second, you can have different symbols to represent the instrument. So circles, squares, different kinds of squares. All right, let's look at this. Let's find a circle. That's a circle, right? What does that mean? That's a little circle. Circle means it's a stand-alone instrument. It's a little box you buy, stand-alone. So stand-alone. How about this square? We have a square. We have a square here. We have this here. What is this? Let's find out.
Computer access.
Yes. PLC. PLC. So this is actually a PLC. That's represented PLC. PLC. Well, there are three different: dotted, no line, solid line. So what's the difference? Field location, inaccessible, accessible. This has nothing, so it's a field location. That means it's not inside your building. It's outside in the field, in maybe a block away. Yeah, depends on how big. Yeah. So it's a remote location. It's a PLC in a remote location. This means the PLC probably next door or inside the same room the operator operates. This means inaccessible behind the panel. Okay. So although they have it looks like a very simple diagrams, but it represents different things. Computer function. Okay, that's a computer function. Let's find a computer function. Yeah, that's a computer function. So it's basically says these two controllers are computer. So you have a computer. One computer or two computers? Don't know. Maybe one, maybe two. I don't know. Because actually what it really represents is two control software. It can run on two different computers. They can run on the same computer. So piping and instrumentation diagram. Okay, the last thing I want to show you is the letters. We says T represent temperature. T temperature right here. T temperature. F is flow. R, the second letter. So you have the first letter. Also, you have the second letter. The second letter, if it's a T, the first letter T represents temperature. Second letter T represents transmitter. So this is a transmitter, sensor transmitter, generally attached to a sensor, right? So it will send out the electrical signals, in this case, to the controller. That's electrical. What about this? Electrical? No. Yes. This is electrical. From here to here, electrical. How about from here to here? Not electrical. Hydraulic? No.
Internal system.
Yeah, computer signals. Basically, the computer tells other computer what to do. Because you have two computers here. This computer make a decision and tell the other computer what to do. Okay, computer connections. All right. Okay, the last thing I want to have another thing. What about this guy right here? Right there. Right here. Math operations, square root, The output is the square root of inputs. Multiplication, division, and a random function. So we actually have a square root extractor. We call square root extractor. So we do some mathematical calculations right here. All right, my goodness. Is that 1 hour passed? We're unable to finish. I think I just stop here. Too much material. I don't want everybody to be overload with too much. I try to cover all 8, but unfortunately, it's too much for Carrie. We already 2 hours. 2 hours. So we will stop right here. Actually, chapter 1 is a big chapter. So much information. The next 2 material will be math, another math. So we're talking about math. So we'll pick up next week. Topic number 7, topic number 8. As far as the lab is concerned, I'm still working on it. Hopefully, I will meet you on the 3rd week in the parking lot. Okay, maybe not 3rd week. I have something else coming up. So, okay, we will talk about. But anyway, this week we don't have labs. Next week, we will decide. Okay.
The lab's gonna be on campus.
Yes, we will do it on the parking lot, outside, on campus, in person.
What are we gonna do in November?
You put on a jacket.
All right.
All right.
Yeah. All right. Well, I'll be here in an hour.
Okay. Any other questions? Any other?
Is there anything to do for the chapters?
So much material. Please read everything. Those are all good test materials. I have, the midterm or the quizzes.
So the quizzes, are those just like every chapter or every couple of chapters?
Random, kind of random. Because most people do it offline, I will give it on Canvas. Just check Canvas frequently. Yeah, I will probably put it on Canvas.
Okay.
That will be kind of like your homework, because if you want to finish the quiz, most likely multiple choices, you need to read the book, so make the right choice.
All right, thank you.
And are you gonna assign any homework?
Today, no homework.
No, not today, but throughout the semester.
Yeah, anything is flexible. I never say never. Anything is possible.
Sounds good.
All right.
All right. We'll see you. I'll see you in an hour.
Really? Wow. I have to hurry up. Eat something junk food and
Yeah, me too.
get back to you. Yeah. All right. See you. Bye-bye.
Bye.